Hey, hello, this is Bob Jackson. We're back at SC201. This is chapter 8, and this is my stuff. This stuff I like. This is where chemistry starts in this book, in this course. I spent the greatest length of time as a chemistry teacher, and it is by far the my favorite to teach. And I think chemistry is, of course, important for people to learn, but chemistry is the basis of so many things and can once people get a good knowledge of chemistry, they can go so many different directions, from going into medicine, becoming a doctor, become anything in the medical field. I mean, nursing anymore. You have to take several chemistry classes. Or at least a few in college to become a nurse. But if you're going on to med school and medical research, there's a whole lot of chemistry that you have to take. But then if you're into engineering, whether it be civil engineering or mechanical engineering or any of those areas, involves a good deal of chemistry anymore. But then if you go work for the state, there's a whole lot of environmental type jobs anymore that where you work for the state or DNR or whatever. They do a lot of water quality studies and in agriculture as far as analyzing the field conditions in the soils and so forth. It's all chemistry. So I mean, chemistry has far reaches, and it's just important. And anymore, we're wanting to reach down to the lower levels and teach some very basic chemistry concepts, and it makes it so much easier for the kids to learn chemistry at higher levels. And chemistry's fun. There's a lot of really neat things you can do in chemistry. I mean, playing with chemistry is neat. And of course, there's bad sides of it where they blow stuff up, but there's a lot of neat and fun stuff with chemistry. Okay, so what I'm going to do, we're going to, instead of doing, for those of you that are taking this course online, because I make this video available also to my face-to-face students, the campus students. But if you're taking it online, you're usually covering 2 chapters a week. Since we're hitting chemistry, you're just getting 1 chapter this week. I'm not going to do chapters 8 and 9 because I think it's way too much to put at you and do a decent job with in teaching. So you'll just be doing chapter 8 and just doing your digital notebook on chapter 8, and then we'll hit chapter 9, which probably means by the end of the 8 weeks, we don't get through what says on the syllabus. But I think chemistry is one of the things that's too important. So that's what we're going to do. Okay, so the main concepts we're going to hit here, if you take a look at the PowerPoint now, are physical changes, physical properties. That's some very basic chemistry type stuff. We're going to talk very basics of atomic structure. I mean, if you get into atomic structure deep, then you get into nuclear chemistry. We're just going to try to teach kids what atoms look like and what's inside atoms. Okay, and then the periodic table. We're not going to go to where we're doing a whole bunch of math and everything. If you've had a good chemistry class in high school and you got into doing stoichiometry and so forth, using the numbers off the periodic table, the gram atomic masses, gram formula masses, and so forth, we aren't going that deep into it. We're just going to try to get kids to know and get them introduced to the periodic table, what's on the periodic table, and somewhat how it's arranged. We're not going deep, a deep dive into it. We're going to do talk about elements, mixtures, and compounds. And as we get into the compounds, going to have you name compounds a little bit, just very basically, some very basic common compounds that you can come across, most of them in everyday life. Okay, so that's what we're going to do. Let's move right along through this. Okay, we start with physical changes. These are some of the most common things that you can see in the outside world around, and you can show kids this very easily. And now my face-to-face students will be doing some labs in class that they actually do with their students. And then I'm gonna have there are some suggested ones on the D2L course for those in the face, or those of you in the online course, can go to, and they're good. Or one of them's where they're making ice cream, in a bag. The other's pops and popcorn. That's doing physical changes. Okay, so physical changes occur when substances change state or form, but they do not change their chemical composition. Okay, it stays the same thing, no matter what. One of the most common ones by far is water. If you take a look here, you got an ice cube. Ice cube's melting. It's still water. On the ground right there, there's water. Okay, if it sits for a long enough time, then that water vaporizes into the air, but it's still water. It never changes what it is. That's a key thing with the physical change, and that's what we want to teach the kiddos is physical changes. The substance never becomes something else. If it changes and becomes something else, then we call it next chapter a chemical change. And we're not going to get into chemical changes in this chapter, just to keep it simple. Okay, if we take salt and we dissolve it in water, that's a physical change. It's not changing what it is. It's just getting dissolved anytime. If you take tea and dissolve it in water, or you make an actual tea, if you take powdered chocolate milk and put it in milk and stir it around, that's a physical change. So that's what you teach the kiddos. It's not changing what it is, because if I boil that water away, the salt will be left sitting in the bottom. And that is an activity you can do with kids as well. Okay, so this on the outside of this cup, and this is something for you to take advantage of when you're sitting in class and you're the teacher and you got the drink up there on your desk. Then take the opportunity, even maybe though you're not on the unit, and say, ask them what that is on the outside of the cup, and say where'd that come from. Someone will try to say it come inside the cup from the ice or whatever. It's condensation, and it comes from the humidity in the air. When it hit the cold cup, you had the phase change. That's a physical change. Okay, so that's something to teach students. Okay, you got condensation right here on this window. Okay, where did the moisture come from? Where did the water come from? It come from outside in the air. When the temperature cooled, it condensated on that window. It stayed water, whether it was in the air where you couldn't see it or on the window. That's what you teach kids. This one, fun to have parties and kids get to see it at some point in time. That's solid dry ice. You put it down in a cauldron of water and that happens. It makes the what looks like the water's boiling. It's not, but this is, okay, the dry ice is subliming away like crazy. But it actually, when you put it down in water, it actually goes right to a boiling point, okay, and creates the steam, okay, that you see. But dry ice is solid carbon dioxide, but it's just going through a physical change there. Looks wild and decent and fun to play with. Okay, what's snow? Snow on the ground is water. It's frozen, right? Crystallized. Physical change. That's where you teach students. That's a physical change we see every year around here. Okay, to some amount. Go up in the mountains, there can be a bunch of it. Okay, and then ice cream. Okay, and like I said, my students I'm gonna have in class, we're gonna make some ice cream in a bag. When it's melting like that, this is a physical change. Now it lays around a while, a few days in the same spot and starts looking green. That's chemical change. But that's physical change. Okay, so we're showing examples of physical changes. Physical changes occur without changing what the substance is. Okay, moving right along. Okay, here's some more examples. We're boiling water. It's a physical change. If we're freezing water, this is a neat thing to do. If you get a day and you're teaching where you're close to where you can go outside, you can, if you're not everywhere has the cold enough temperature for it. But if you get down, it's negative 15 degrees out or negative 10 degrees outside, take and get you some of the bubbles and blow them in there. And if you blow them in there and it's that cold, they freeze in the air. and then they'll land like that. I do it every time we ever have really cold temperatures, just play around. But that's just a physical change. But it's really cool to take the bubbles and blow them in the air and watch them freeze. Physical changes. There's the subliming again, that's dry ice. We say it's subliming, that's where I'm just on this page trying to show you the terms. We say this is freezing, this is boiling, this is subliming. They are physical changes. This is melting, physical change. You want to get them to know the terms with what they are, physical changes. Okay, grinding something up, I think that's probably cinnamon. I think those are cinnamon sticks. If you just grind it up, it never changes what it is. It's just a powder instead of cinnamon sticks. Okay, it's just ground up. If we shred paper up, it's still paper. Okay, physical change. Dissolving salt and water. Okay, dissolving. It doesn't matter what it is, whether it's salt, whether it's chocolate milk, whether it's whatever, it's dissolving. It's a physical change. Evaporating. Anytime anything, it doesn't matter whether it's water or alcohol or gasoline. Gasoline vaporizes so easily. That's what makes it so dangerous. That's physical change. Okay, now evaporating is something even like ammonia, pure ammonia, and anhydrous ammonia the farmers put on vaporizes so easily it can be deadly if it's something that hurts your lungs. So some physical change properties can be dangerous. Okay, so that's physical changes. Okay, let's move along. Next, we have physical properties. Okay, you have physical changes and you have physical properties. Properties are properties of the substances. So physical properties can be measured or observed without changing the identity of the substance. And they can be used to identify what the substance is. When you find out the physical properties of a substance, like if you're working in a criminology lab, that's what they do. They identify substances by their physical properties, known physical properties that they can look up. Okay, and what's listed on this page here on the PowerPoint are some key physical properties that we use to identify substances by their boiling points, their freezing points, their melting points. Those are key ones. When you're saying points, they are temperatures at which they do what we said. Boiling points, temperature, something boils. Freezing points, temperature, something freezes. And the melting point is temperature, something melts. Okay, so for like water, it's 100 degrees Celsius for a boiling point, or 212 Fahrenheit. Okay, I can use that to identify water. Okay, but if I take ethyl alcohol, drinking alcohol, it's about 70 degrees Celsius rather than 100 that its boiling point is. You can look it up for exactly what all our liquids, all our substances have set boiling, freezing, and melting points, unless they're mixtures. As long as a pure substance, they have set boiling points. Okay, luster is shininess. So you can identify something pretty easily if it is a like the lid on this. The lid on this, it's shiny. So you can tell me right now it's a metal. Now what metal it is, you don't know, but you can tell me it's a metal just by seeing that. If you see this pen right here, you can tell me that's a metal right there on the clip because it's nice and shiny. It has a luster. We recognize metals by that. Okay, so luster is a physical property. Solubility is a physical property. That's the one that tells us about substances dissolving. Solubility tells us how much of a substance we can dissolve in a given amount of solution. It's the amount of substance that we can dissolve into a given amount of solution. So like you can only get like 25 grams of sugar dissolved in, say, 50 milliliters of water. I mean, you can look it up. Okay, all our substances that dissolve will have a given solubility at a given temperature. Okay, so all you got to know for now is it is the amount of substance that will dissolve in a given amount of solution. Okay, then you have the two types of conductivity. You have conductivity of heat where if it's particularly these are metals typically, it will allow heat to move through it. Okay, from one end to another. That's why you use a metal pan to cook with, because the heat will conduct through it. Okay, but you also don't want to stick a metal stick in the fire and then grab a hold of it after it's been there for a while because of the heat conductivity. Okay, but then we also use certain wires for electricity because they conduct electricity well, like copper does, aluminum does. Okay, and there are key metals. Silver would too, and so would gold, but they're a little bit too expensive to use for electrical cords. Okay, ductility is a property of metals, and it is the ability to make that metal into a wire. Ductility is a property a metal has if it can be made into a wire. Okay, not all metals can be made into a wire. Like you're not going to take a zinc and make it into a wire. It don't have that property. Okay, so when a metal has the property of ductility, it can be made into a wire. Malleability is also of a metal, but it's where it can be made into sheet metal. It can be pounded into sheets, so like aluminum. Okay, aluminum is one by far most common. But then you also have stainless steel. Okay, stainless is pretty common. You can have copper sheets. Okay, copper is malleable. You make sheets of copper, okay, to put on things. But aluminum is probably the most common galvanized metal, which is actually a mixture, but it's malleable and can be made into sheets. Okay, so ductility, make into a wire, malleability, make into sheets. And that's, they're both, they are properties of metals. Okay, and only metals really. And then density, we've learned back in one of the other chapters, is the mass per unit volume. But it's also a physical property of substances because you can use a substance density to identify it. Okay, so density is actually a really important one for identifying. Density is a big one, along with boiling, freezing, and melting points for identifying compounds. But you can tell some by whether they're these here, the conductivity factors, ductility or malleability, because that gets you down to the types of metals. Okay, let's go to the next one. Okay, other physical properties that are a whole lot more common and that people know that they don't even know they know them. If you're talking about the color of something, red, blue, yellow, green, so forth, it's a physical property. It's not a chemical property, it's physical properties. How hard something is, okay, or how soft it is too. That's not up here, but the hardness of a substance is a physical property. The size of them, the weight of them, the mass of them, the volume of them, those are all physical properties. The length, the surface area, any of those measurements, okay, are physical properties. Okay, they're just not, you can't really use those. You can't even use, you can use color somewhat, but there are a whole lot, particularly when you get to white stuff. There's a whole lot of white stuff out there. You can't use color to do a whole lot of identifying in chemistry. Okay, so those are the key physical properties we've got through. Now then you can take those physical properties and divide them into two entities: intensive properties and extensive properties. Intensive, N. It totally depends what the substance is. So it's in it, I always say. Intensive, N, depends what it is. Okay. It totally depends what it is. Extensive properties has nothing to do with what the substance is. Okay, so it's outside. Okay, intensive in, it depends on what the substance is. Extensive out, so it doesn't matter what the substance is. Okay, and now the best way to do it is to break it down and show you examples of the stuff. But realize these are two types, two categories of physical properties, because we're still talking physical properties. Okay, intensive properties are things like taste, color, hardness, boiling point, melting point, density, even, malleability, ductility, conductivity, all of those. Okay, which some of those are hit over here. Okay, that's why I put both these different charts up there. One don't have them all. in it. Okay, those, if they can be used to identify the substance, they are intensive properties. Okay, if they cannot be used to identify the substance, they're extensive properties. So if you're measuring in any kind of way, length, width, surface area, volume, mass, weight, those are all extensive properties. And it doesn't matter what it is, you just put it on a scale and you're weighing it. Okay, but intensive properties totally depend what they are. Okay, that's it, and it shows you examples on each one of these charts. Okay, it shows you there is some overlap between them, but intensive are the key ones used for identification purposes. Okay, so moving on. Okay, now we're going to basic atomic structure, and this is going to be the most of it right here because we're not going into nuclear chemistry with elementary school. Okay, basic atomic structure. The main thing we want to be teaching is we have inside what's inside an atom. Okay, when we're talking an atom, the atom is made up of protons, neutrons, and electrons. The protons and neutrons are in the nucleus. Okay, just want to get them used to looking at diagrams like this and recognize what is there. Very basically, very, very simple. Okay, so protons are the positives and neutrons are neutral. Okay, and that's the charges which we talked actually in chapter 6 with electricity. And that's where electricity comes from, these electrons out here. So then outside the nucleus of the atom, in orbits about the nucleus are electrons. Okay, but they're all in an atom. Okay, the electrons are moving about that nucleus. Okay, and electrons, you can even explain to them, as we see with electricity and static electricity, are easy, relatively easy to get them moving. Okay, and get some to actually leave the atoms do the electricity thing for us. But your protons and neutrons stay there. If they're going out of there, you got yourself a nuclear reaction. That's why they're so dangerous. Okay, and what you can explain to kids. Okay, so that's basic atomic structure. Okay, now then, within the basic atomic structure, you can start, and this we're just going to teach you very basic. We're not going to go into very deep. If you take the number of neutrons and the number of protons that a substance has in it and add them together, you get what's called its mass number. Okay, and you can actually give your students some simple problems on these. Okay, if I know that carbon has 6 neutrons and it has 6 protons, it's going to have a mass number 12. Okay, I mean, it's that easy, you just add them up. But you also have carbon atoms like carbon 14 that has 6 protons and 8 neutrons. So 6 plus 8 is 14. Okay, you can have different types of this same chemical element, and that's what we call isotopes. Isotopes are different forms of the same element with a different number of neutrons, and you tell it by their mass number. Okay, when you're getting the mass number, because they're going to have a different number of neutrons than protons, all the different isotopes. Okay, then average atomic mass is what we're going to see when we go to the next slide on the periodic table. Average atomic mass is what you see on the periodic table. It is where the mass numbers for all the chemical elements have been averaged relative to their isotope. So all you really got to tell your kids at elementary, it's an average. That's why, like mass numbers, if you take protons and neutrons and add them together, you can never get a number that has decimal points, but they'll see decimal points on the periodic table because they're average atomic masses. Okay, of all the isotopes of that element. Okay, moving along, here's your periodic table. Okay, now we're not going to go deep into the periodic table. There's just going to be key things I'd like for you to start teaching students. And we really need to get the students learning these things at a little bit younger ages than maybe what we typically do, just because, and the basic stuff they can get. Okay, for one, this periodic table that I have on here is clickable. If you click on it, you're going to go online to one of my favorite places, and I gotta get a drug over here. Okay, ptable.com. Okay, and this gets you to an interactive periodic table to where you can take the kids and you can do what you want with it. And say, all right, we want to know something about, let's say gold. Click on, if you click on it, then it's gonna pull gold up. Whoop, another move my mouse around. I'm on gold. If you look over here to the side, then you'll see gold, and you'll see down here all the information. I know at elementary, you're not gonna go electronegativity, all that, but here's the melting points and boiling points and so forth, that's saying that you could use to identify. Those don't change. Okay, that's gonna be right here. Okay, now then you also go up here and click on this, and it should take you to Wikipedia where you can show them a picture of it. And you can, if you wanted, like 5th grade, you wanted to have them do some research projects and find what some of these elements are used for, right here's where you could have them go. Okay, and it would be a good project. Okay, so you can drill in on the ptable.com into these elements, and it makes a good project. Where you got them all on the same page and they're on the computer, and you can have them look up what they use carbon for. And that's where we don't have to do that much chemistry. We could have them do little projects in like 5th grade and just assign each set of kids an element to find out what they can about. They can do that. Okay, other than that, the key things I'd like for students do, and that's what you can use with ptable.com so easy. The metals, all right, where's the metals at on the periodic table? Well, if I come up here and put my mouse on metals, it will highlight just the metals on the periodic table, which you'll see they're all the ones over here, okay, and down here. They're all of these, which are divided by this line that comes right down through here. Okay, but if you go here, it will light it up or highlight just then. Then you have non-metals. That's the ones over here on this side. Okay, these are the non-metals. There's by far more metals than there are non-metals. Okay, then the ones I'd like for them to know are the noble gases. They're the noble gases because they virtually react with nothing. That's why we put them in things like we do. We put argon in light bulbs because it's inert. It doesn't react with anything. Okay, but we also have neon lights and so forth. Okay, but those are the inert gases that react with that, and we call them noble gases. So I'd like for you to know those. Okay, and it'd be nice if you're talking to students. Then you have the alkali metals. Like people to know these as alkalis, know the alkali metals, because they're some of the most dangerous ones on the periodic table: lithium, sodium, potassium. Okay, if you read about them, you'll see they're very reactive with water and they're very dangerous, actually. Francium, okay, all of them down this, these are all except for hydrogen. It's the only one they're not. From here down, they are the alkali metals. Okay, so like know them, and then the it'd be nice to know the over here these guys, seeing where they've got it. Yeah, well, no, they don't. These are the halogens, right down to chlorine, chlorine, bromine, which chlorine by far is the most common one used as a bleaching agent and sterilizing in the real world. The halogens here. And that's all I would think to teach you got. Noble gases, halogens, alkalis, metals, and then non-metals. You could teach metalloids if you wanted to. They're right down through here. The most important metalloid of all of them makes computer industry possible is silicon. Okay, because it makes semiconductors out of it. But gallium arsenide is a lot of things are made out of it as well. Arsenide's here, gallium's right there. They're actually used together to make diodes and so forth. Okay, so that's the ptable.com and the main things I'd like for people to know about that. Okay, so there it is on my slide, and just realize if you go to slideshow, you click on it, you go to ptable.com. Okay, now here's where I've just kind of put the chemical elements up there, pictures of them, so you can kind of show some of them. There's not as neat to use as the ptable.com, but it's got the elements in like a pictogram or whatever you want to call it, where it shows you what they are. Okay, but of course, on the periodic table, we have the chemical elements. The chemical elements are the simplest forms of matter. Okay, they cannot be broken down any further. Okay, and there are 118 of them, as we know now, and if you go back to periodic table, you can see that and show the students that we have 118. All of these over 100, with the numbers over 100, are all synthetic, actually. Okay, not natural. Okay, so they have that. We may have more than 118 now. I really don't know, because that changes through time. Okay, so elements are the simplest form of matter that cannot be broken down. They're also what we see on the periodic table. Okay, that's the main thing to teach them, nothing hard. Okay, then we'll go into the different things that you can have. You can have elements, you can have mixtures, and you can have compounds. And I like for kids, because these are all around people, and they should start learning what they are. Mixtures are physical combinations of elements or compounds, or they're just mixed together. And that's by far the most common stuff around us. We eat it, drink it, everything. We deal with it every day. Okay, so mixtures can then be categorized as homogeneous or heterogeneous. Homo same, hetero different. Okay, here's I have some examples of homogeneous mixtures over here and hetero over here, and they're pretty obvious, the differences. Okay, and one other thing to point out here, mixtures are never pure substances. Mixtures are mixtures. Pure substances are the other two things, elements and compounds. Okay, elements are pure substances and compounds are pure substances, but mixtures never are. Okay, so homogeneous mixtures, milk, Coca-Cola, coffee, lemonade, they're all very consistent color throughout. If you see more than one color in them, whether it's just 2 colors or 3 or 10, it's heterogeneous. But if it's one color throughout, it's homogeneous. This is homogenized milk. That's why they call it homogenized milk. Okay, it's homogeneous. Okay, these are heterogeneous. You see more than one color present there. And they're a mixture because they're different things mixed together. Okay, these are different, and I didn't say that over here. These are mixtures because they are different things. If you boil that milk, you'll find out there are different things in it. Okay, and the same thing with Coke. We know there's caffeine, there's sugar, there's different things in that Coke that makes a Coke, and the same thing with the lemonade. So you want to point that out to kids. Mixtures are always made up of different things mixed together. And same thing with these items over here, they are mixtures. But these are more obvious to see that they're mixtures. Okay, go to the next one. Then we'll get to compounds. Here's compounds. Okay, compounds are 2 or more chemical elements that are chemically combined together. 2 or more chemical elements combined together to make one substance. Okay, compounds are pure substances, and there's zillions of them now. We're synthetically making all kinds of compounds every day. Okay, we're not going into the complex ones, just easy. Water is a compound, most common compound we know and need every day. H2O, water. Carbon dioxide that's in the air that's leading to global warming and all. It's a compound. Sugar is a compound. Sodium chloride, salt, it's a compound. Baking soda used at home, whether it's used for cleaning purposes or what, or cooking, it is a compound. Alcohol of any type, we'll keep it clean with elementary isopropyl rubbing alcohol. It's a compound. Lime that you use either on the garden or farmers use it, it's a compound. Lime's a compound. Okay, so we're just showing examples of compounds on that screen. Okay, so now I want to take you to naming simple ionic compounds, and we're just staying extremely basic. Your main tool for doing this is the periodic table. Okay, and that's where I brought you back to this. Okay, you can always have a periodic table in front of you. You want to have a periodic table in front of you when you're naming the compounds. Okay, you're going to go and realize these are metals, these are non-metals. Metals are never going to change their name in naming. Non-metals, you're going to put IDE endings on them in both types of compounds. You'll get the names here, like chlorine will become chloride, sulfur will become sulfide, oxygen will become oxide, okay? And remember, these are never going to be, because they don't react, okay? Iodide, bromide, and so forth. You'll see them on here as like chlorine, but you're going to call it chloride when you name it, okay? So let's go back to the screen where it is. Whoop. Okay, so here we have two types of compounds, basic compounds. There's actually more than two, but we're just keeping it simple for elementary school. We have ionic compounds, we have molecular compounds. Okay, so this screen's on ionic compounds. Ionic compounds are made up of a metal and a non-metal from the periodic table. And now that's what I was saying, when you go to naming them, the metal is name always stays the same as on periodic table. So that makes it easy. Just read it off there and write it down, and you got it. And that's where upper level elementary kids can definitely do this. Okay, so sodium chloride. Okay, I look it up on the periodic table, it's sodium. I look this up on periodic table, it's chlorine. I'm going to change the ending to IDE, sodium chloride. This is barium, this is oxygen, so I'm going to call it barium oxide. This is magnesium. This is fluorine, so I'm going to call it magnesium fluoride. Okay, pretty easy stuff. Okay, if there's any numbers in them on ionic compounds, you don't use them in the names. You will with molecular compounds, not on these. So if it says simple ionic compounds, you don't do nothing with the numbers to name them. Okay, so it'd be wrong to call this magnesium difluoride because it's just magnesium fluoride. It's the way you name ionic compounds. Okay, now if I go to the next screen, these are simple molecular compounds. Okay, molecular compounds are always just made up of non-metals. Okay, you don't see metals in them. There are a few in the world, but very few molecular compounds have metals in them. Okay, so that's where you recognize them. They just have non-metals in them. When you have the periodic table in them, on these, you will see over on this side of the table, they're always just these elements over here. Okay, they do not have metals in them. Okay, so when you have these, the naming method here tells you you're going to use prefixes for these numbers in the name. That's how we differentiate when we name between molecular and ionic compounds. We're only for elementary school purposes, because you can go on up to numbers 10 or 12. We're just going to stay with ones that have 5 or below, because we want to keep it simple. Okay, so mono, di, tri, tetra, penta. And most elementary kids know these prefixes. They do. Okay, mono 1, di 2, tri 3, tetra 4, and penta 5. Okay, that's how it's going. So you put these on the elements as prefixes. So this is carbon dioxide. I'm using the same technique as before. The oxygen, I changed to IDE. I put the di here because there's 2 oxygens. So I'm saying this is a molecular compound, carbon with 2 oxygens, carbon dioxide. Then I take nitrogen trioxide, nitrogen trioxide. There's a 3 there. I'm just saying exactly what's here. Diphosphorus, there's 2 phosphoruses, pentaoxide. There's 5 oxygens, so I'm saying there's pentaoxide, 5 oxygens. Okay, and that's it. Okay, that takes us all the way through the Introductory to Chemistry, Chapter 8, and wraps it up for this week. Okay, have a good week.